Mr. Wei-Han Lien, the civil architect at Tenstorrent, who represents on beyond innovation required but to mass adoption with mature ideas. Welcome. Please welcome him.
Tenstorrent シニアフェロー、ウェン・ハン・リエン様より、イノベーションを超えて成熟した IP による RISC-V の大量導入への道、よろしくお願いいたします。
My apology. Good morning, everyone. So it's always good to come back. So this is my third time talking this conference. I always like to coming back to this conference just because you actually, first, like, of course, great energy from Japanese people about this topic. But you guys are the only organization that has twice a year kind of a RISC-V summit. That means there's a huge interest on this topic. And then, and you also forced me to actually reflecting every year when I talk to you guys, what exactly need to be achieving for this RISC-V program we actually have in the Tenstorrent. So 2 years ago, I talked about basically Tenstorrent kind of designing the process, right? Roadmap, how we actually think about the CPU architecture. And then last year, I started talking about how to using RISC-V in AI application, right? And then what kind of important role you play in the AI, not only for Tenstorrent, but for everything around the world. But this year, I started thinking, reflecting, yeah, this is a very interesting conceptually, right, about RISC-V architecture, its application, but we have to break through this talking, right? My main topic here today is that we really need to see real implementation on the RISC-V, high-performance RISC-V to substantiate that this, effort which has happened 15 years ago from, UC Berkeley is actually real, right? So that's why I come with this topic, say beyond innovation, RISC-V past mass adaptation, right, with a mature IP. The key is actually mature IP. Right? We want to see a real board, real design, real high performance code to substantiate this momentum is actually true. My name is Wei-Han Lien. I'm the chief architect for Tenstorrent. One thing I want to talk to you about is that how we actually get to this place, right, in the whole AI computation ecosystem. Why we are here today. So you look on the whole semiconductor revolution, computer revolution, which is deeply tied to the semiconductor. Starting around 1947, you invent the transistor, and then there's two paths, right, going on. One is on the top, this is computation innovation, miniaturization because of the transistor. I still remember, like, early on, PDP-11, IBM, C17 is like ginormous box. But later, it's actually become like a PC and mobile computing. It's all because of miniaturization of the transistor technology. So you can see that on the upper side, you have PDP-11, right, 1970, and then eventually go to 1998. The miniaturization going to the PC, replacing those big mainframe, mini computer in the world in a significant way. Right, so back, selling to digital, that's how I kind of identify as a way that PC personal computer is actually taking, replacing the personal computing. And then you go further, then 2007, I was working, so we acquired Apple, we started working on the mobile computing, right? That's where really we call personalized computing is possible because you can carry that device everywhere. You're going to shopping, you're going to sleep, right? You go everywhere, you carry that device with you. So on the bottom side is about connectivity, right? So transistor also helping you with the connectivity, right? Networking, right? So coming from Netscape browser 1993, then you start have the internet concept. Then 2000, where the 3G wireless starting, populated, in the world, that's where you're starting what we call personal connectivity. So that colliding with the 2007 personal computing, mobile computing by Apple, it generated this revolution, right? But mobile computing, now everybody can carry that. What's the result of that is that you generate tons of data because you carry everywhere and then you send the data to data center, how you browse, how you use, how you doing the advertisement. You generate tons of data. So Apple 2008 until 2012, suddenly people started to notice that there's a huge amount of data you can actually mine the gold inside the data. And that's where the AI start taking off, 2012. Right? You see the model accelerating, right? Because people notice that the huge amount of data generated by the mobile computing stuff can collectively ensure you has information about personal behavior, shopping behavior, everything. Right. So that's driving the AI. So AI, you can see AI completely take off after 2012. New model coming up. I was in the school 1995. I studying neural network. By that time, it basically is a theory, right? There's no data you can train. There's nothing you can actually, even the technology to implement the computation requirement. But 2012, that's where the things start taking off. And then, of course, 2017, you have Transformer. And then 2023, you have ChatGPT 3 that start populating the, AI revolution. So you can see this is a turn, and then data center has enough computation to train the model with a huge amount of data and start using that information going back to the personal computing and drive the usage of your life. So you can see this virtual cycle about personal computer generate data center generate a lot of using that data information and generating the model and information and going back to the mobile computing you use every day and driving everything you use today. So this virtual cycle about high performance computer, right, large scale computer in 2022 and then going back to the personal, AI computation is actually a circle there, right, interesting circle. And then what this interesting circle is that in the future, right, the direction of the AI is actually we call personalization. So AI will go with you, personalize your DNA, understand what kind of drug you made to you, personalize your kids' education based on their capability, interests, and time frame, right? So all the information now going back to you, and then you will be living with the AI every day, right? Using your information, train the model so to make AI serving you better. So that's where we take it. So I think the future AI, just because you have to personalize, right? So we have 6 billion people in the world, everybody has their own need. Then the personalization of the AI for yourself, you actually represent the huge amount of computation requirement. So that's why I say in the future, AI has to be ubiquitous, right? It has to be everywhere. So you will be a robot person will go with you, grow with you, right? About what you're going to do and learn from you and provide intimacy information, helping around everything. But this requires huge amount of compute. You require local compute, you require edge compute. It's just impossible in the future, right, to send all the data information back to the data center. It's uneconomical, infrastructure is too expensive. You know that the self-driving car, right, autonomous driving, self-driving car, each day when they're walking on the road generate 7 terabytes of information. So that information cannot be sent to data center. It had to be locally used, locally trained, based on the information they needed, right? So you have to be localized. So that's mean in all layer of the computation, right? For AI computation has to be exist somewhere in the cloud, in the edge, and then also maybe in your home with your robot with you. So you have this vision about ubiquitous of AI compute, then you think about what kind of hardware computation system you want to build for that. So last year I talked to why this is RISC-V is perfect for this scenario, right? Because now you think about ubiquitous AI compute, then you need processor everywhere, right? On your client side, on the edge, right? On the car, and also on the data center, right? So every segment you actually need CPU in there. So you also impose a different design constraint and different application requirement. for doing that, then RISC-V is perfect for that, right? Because you can do scalable design because you just take their license. You can implement any arbitrary, process design based on their performance, power, and the requirement, right? It's extensible, right? You can take the ISR doing the extension and fulfill your personal need or like the specific application need on the layer you are interested. It's efficient because you don't using bigger compute not fitting for smaller compute, right? So you will be customizing, so your implementation will be very efficient. You're also stable, right? A lot of people, right, building the hardware is concerning about the supplier stability, right? Because if I've been monopolized by one, like ARM, right, for example, IP, I don't have any negotiation power and I cannot go anywhere, and then they can stop license to me, just like Qualcomm case, right? So this is a perfect architecture now for this ubiquitous AI computation. However, right, so we've been talking about all the benefit of the RISC-V architecture and then why this is important in this current AI computation challenge. But however, you do need a very, very strong implementation. If you look on the history, right, year 2000, you have PC actually replace workstation. I don't know, many of people are probably too young to know, but I was at that time as an engineer. My desktop has like a sound workstation costing $10,000 at that time. It's equivalent to a car. But then the PC actually coming in with 3,000 price tag with the Linux and doing as well in the logic synthesis, right? And of course, that transition will be very fast. After that, people finding, oh, Intel has a great implementation on the AI cycle Pentium 2, and Linux just taking off open source operating system. It immediately crashing the sound, the silicon graphic, digital alpha, workstation, they disappear like crazy, right? So open architecture drive innovation, but the underneath hardware supporting that open source ecosystem has to be there and has to be power efficient, has to be price performance right to enable that replacement, right? So similar thing need to happen on RISC-V architecture. We need a good implementation at this point to justify our existence replacing ARM architecture in x86. So this is basically the picture say we are in a crossroad, right? So RISC-V has been starting on UC Berkeley 2010, now it's 15 years effort there. But most of the thing we do here is actually on the embedded space, IoT space, low-end processor. It's very fragmented, very niche, right? In the niche market. I think this is about time we need to have high performance RISC-V architecture implementation there with the older machine, right? And then CPU with a high memory bandwidth for high-end, computation. We need to have, because without the platform, right, you can optimize the compiler, firmware, system, software stack. That's only the way you can actually move this software ecosystem forward with a very good high performance implementation. And then, of course, the application like a scalable heterogeneous compute in HPC AI, in networking, you only high performance RISC-V CPU. So without this kind of investment, right, RISC-V will be confined to a low-end and very niche market. So Tenstorrent as a company, right, we are building a computation technology supporting for the future AI. We don't believe that today AI algorithm like transformer will be the algorithm 10 years from now. Everybody know Hugging Face, right? Every day they have thousands of new AI model being uploaded to that website. And who knows which one going to be next transformer. So if you actually fixated on one algorithm you are building, and then you design the hardware super optimized for that, you may be going to the wrong place, right? So you cannot bet in a company's strategy or long-term view based on one algorithm you have today, which is most popular. So what Tenstorrent do is we're building the technology being able to build the most fast computer, right? So that basic technology, including the CPU, RISC-V CPU, opens hardware architecture, and also our Tensor CPU, Tensor AI hardware, right? So we have this 2K computation technology, but my team is building auxiliary technology on SoC side, on the PCIe, networking, memory, fabric, and also like thermal power solution, all for design for a great system. And eventually we use all this technology, we start building the chipset technology, right? So we have project with Japan on the AIDC, building the chipset, AIDC project, right? With the Japanese AI chipset, with our CPU chipset working together. And then the fulfillment for all this technology eventually driving to Tenstorrent data center solution, right? You see the chiplet solution and our automobile effort, and then also like Japanese, AIDC project. So you can see the company is actually focused on building the best computation technology, enable us to very adaptively, right, adjusting us for the future computation requirement. So this is one of the implementation that we have to go to Ascalon, right? People you probably will see about is 18 specking. We started working on this about 3 years ago, right? 18 specs, AY auto issue machine, right? So it's pretty advanced, RV23 compatible, but we are close to tape it out, right? Like I say, it's very important now for the RISC-V camp has a great implementation, right? We cannot just keep talking anymore. So Tenstorrent is actually in the process of taping out this chip, right? So you see this is the physical design. So somewhere on the Q3, Q4 this year, we'll tape out this chip, and then it's already performance correlated, right? So we run in the emulation, you're meeting our performance goal, timing is getting close, function is getting close. So I hope next year when I was here, I able to show you guys the chip, right? High performance RISC-V chip on the stage. And then we ourselves, we're using this technology to build in, we call Athena chipset. You can see this chipset has LPDDR5X technology. We also have PCIe Gen 6 32 line, and then you have the die-to-die interface. This is basically a small computer with the 8-core high-performance Ascalon processor. So this is burn 25 watt in SS4, and a lot of people is already showing interest on this. So Tenstorrent will use this technology for our heterogeneous compute. But at the same time, there are a lot of people interested using this chip for development platform for RISC-V, for laptop computer in the RISC-V. Right, so this is our way try to implement the real high performance computing so that we can demonstrate to the world that RISC-V is actually real, right? It's not just a slogan, right? So you can see that there's a 2 implementation usage, right? Tenstorrent will be using that as a heterogeneous compute. So the left-hand one is actually has an AI sitting in the middle and the Athena sitting on the side. You can use that as the CPU as a self-hosting, right? Running operating system, running networking, self-hosting, replacing the AMD processor, right? Or we're using as part of the AI computation because the close vicinity that they are tightly coupled with the AI computation, they can actually participate in the AI computation, like you see here, in one single socket, single package. Right? Second one is actually the development board. We're actually going to design using this chip, right? So it's just single Athena, a high-performance core in there. We're going to build in very cheap, and then we're going to using that to develop, to doing the development board or putting in even the laptop computer, so that people can buy that using it as a development platform. And then you can see the beauty of this technology chip there, right? So you can either using on composing a high-end system. On the other hand, you can use that for the laptop computation. So one design being applied to 2 different places just by the changing of the package. So to even substantiate the effort behind the RISC-V, we not only need a real implementation, we also need a roadmap, right? So it's important to tell people that we continuously invest in this technology. We are catching up with the ARM. So you see these 2 trend line there, which I draw based on all the data point provided on the internet for the Apple, right? So the one above red line is the Apple trend line. So you see the vertical line here is actually speccing per gigahertz. So that means it's architecture, microarchitecture performance, right? So higher performance, more complex it is, and more hardware you need to use to implement that. On the bottom horizontal lines tell the timeline, right? You can see that the upper one is the Apple trend line, the lower one is the ARM trend line. You can see Apple is always leading, just because Apple is always using the latest technology to drive in the iPhone. So they have 2 generations in general process lead compared to the adopter of the ARM architecture. So our strategy, right, our roadmap here is shown in the Ascalon, right? Ascalon is first generation. Next year, we're going to move in that performance point 10% every in yearly cadence, right? So Ascalon plus, Ascalon plus plus will be 21 and will be 23, right, in the next 2 years. So we have team continue doing that. I'm also leading a team basically branching out from this design and putting the highest performance core possible in 2027. So that's called Callandor. That will be 100 performance game compared to the Ascalon core. So we have separate team investigate this 16Y design machine, right? And then we are building a machine that is probably highest performance. As you can see, right, we will actually catch up the Apple trend line in 2027. So when people see this, you know that Tenstorrent is strongly behind the effort of building a high-performance RISC-V in the next 2-3 years. So we will count with the incremental improvement on Ascalon, but also moving the highest performance processor core in the world. So this is basically the Callandor architecture, a brief description. This is 16Y design, 16Y machine, and then we are currently designing AY machine. Yeah, so it has advanced branch predictor, 2 taken branch can be taken, right, predicted. You have decouple front end, right, and then you have micro-arc cache, and the mid-core is a 16Y decode, is almost 100% more decode bandwidth compared to the one in the past. We have register sharing for the power and implementation reason. We have 1 kilobyte, 1 kilo entry of the reorder buffer. Execution unit will have 6 white load store units, ALU 4 branch, 4 vec 256 vector units, basically double from the current size, like 256. And we have F4 FPU. We also are going to support the metric engine. So this is a really high performance design, where it will be even better, right, compared to what Apple have today. So that's our goal for next generation. At the same time, we also moving toward, right, so we talk about extensibility of RISC-V architecture. We're actually going to move this implementation for automobile as well. So the Ascalon processor, right, in the next year, we have team actually porting that to auto-grade satisfy functional safety requirement for the automobile industry. We will start building that IP because Tenstorrent is heavily engaged with the automobile industry, right? So as you people working on automobile industry understand that there's a functional safety requirement. So Tenstorrent is actually building a functional safety, certified version of the Ascalon for going to that market. So you can see that Tenstorrent using all this technology to building the computation requirement for L2, L3, L4, right? It's all based on our key computation technology on CPU, right? And also on the AI. Like our AI architecture is already functional safety qualified. Now we are actually building a version for Ascalon, which is functional safety curve, certified as well in the process of doing that. So with this key computation element, we'll be able to build a scalable computation, right, needed for L2, L3, and L4 autonomous driving system. We also will use this technology to build the heterogeneous compute system for the future neuro-symbolic AI computation. People think this is the future of the AI, right? Combined with the symbolic compute and also AI sub-symbolic compute. So AI will performing the sub-symbolic computation, CPU performing the symbolic computation. And the necessary ingredient for this kind of computation to be successful is actually the latency and also the bandwidth communication between CPU and GPU. So that's why integration of this technology together is important. So the summary I have is that AI will go into personalization, right? So underneath that, so that means AI will be associated with you. Like suppose you imagine there's a robot, right? Go with you every day, grow with you at the age, understand your, change of the interest every day. So it's impossible to send in all that information to data center because the privacy reason, right? Because even there's in future there's a regulation, right? Prohibit people sending the data, your personal data, to the data center. So that's mean this personalization. That's mean the computation, the training, everything need to happen locally for you, and that's why the computation environment has to change with this personal AI computation. So it means that you need an efficient computation on all level of the compute, from the client, edge, and to all the way to data center. So RISC-V, as I say, provide a scalable, open, and also most important, portable. Right? What is portable is that software portability is important, because for all this diverse computation, you don't want to rewrite in software for every layer, right? So Tenstorrent technology provides, scalability and also uniform open source software system comporting among different levels of the computation. So it's critically important for this kind of compute in the future. You will meet the future AI compute challenge, right, with the diverse fundamental technology. That's what Tenstorrent is driving into. Like I mentioned, we are not specific optimize our design for one AI algorithm. We are trying to do is actually build the best general purpose compute AI computation platform, right? So that's why we have to get all those people building CPU, AI, SoC, chipset, right, together to enable that to happen. So I really think it's now about the time that we demonstrate a real working high-performance RISC-V system, because software need a platform to develop it, right, moving this moment forward. So we need that kind of real system to prove it. And Tenstorrent is doing that behind it. We spend millions, hundreds of millions of dollars doing this. So I hope really like next year, right, I will be here and taking our chip, say this is a high-performance RISC-V processor, right? So I keep telling my teams that I'm tired of talking, right? So I want to see a real chip. And next year, maybe I just show like, hey, this is the chip, that's it, right? This is my talk, right? So doing is much better than talking. Last slide. We are hiring in Japan, right? So any young people here interested join Tenstorrent? So Nakono-san is here. He's head of the Japanese, subsidiary of Tenstorrent. We are moving to a new office with 100 people capacity, right? So we have room to hire a lot of engineers. So if you want to working with Ishii-san, right, the coolest, architect in Japan, and also Camille, right, please talk to us. Yeah, thank you very much.
Thank you, Mr. Lien, for the insightful presentation. Do you have a question for the Mr. Lien?
100. Yeah. So currently we have about 10 people already here, and then we keep hiring. Yeah.
It's probably have to say that what kind of design there.
Okay.
What is the
So the first project we are supporting is this AIDC project, which is porting our design to Rapidas 2 nanometer, right, with our CPU chiplet. So the Athena chiplet will be ported to 2 nanometer and working with the AIDC, AI compute together. So that's the first effort. And I do really want to build in the auto, design capability in Japan, because I think that matching Japanese need from the auto industry really well. And that's another project we are working on. But there's a lot of projects actually coming in Tenstorrent. So I think we can definitely use the talent in Japan. Yeah. So we are eagerly to grow, and then we especially want to recruit in the young generation, want to work in the semiconductor industry, right? Yeah.
So let me confirm, the chip designed at design center, Callandor center, will be fabricated at Rapidus, right?
Yes, the first design. The later design, it can go anywhere, like TSMC, Samsung. Yeah. It's all depending on the project need.
Thank you.
Yeah, sure. Any question?
質問のある方は、挙手をお願いいたします。
Okay, thank you. Oh, yeah, there's one more.
Thanks for your presentation. My question would be, what lacks you to get to the goal with the high-performance chips? Is it funding, or is it something else that lacks you to get to that goal?
I personally working on a high-performance chip for my career in Apple, many different places, right? So the key is, of course, is the engineering. Right? Funding in general, like you have good program and then you can talk investor, but the talent is the most important thing. Like I talked to Minister Miti, right, Vice Minister. I say that, yeah, Japan is spending a lot of money building foundry, but eventuality is about the design going to the foundry had to be locally grown. And my experience, like we starting the Apple 2007 with the Apple doesn't have any chip design. It took them almost 20 years to get to today. Training the people, get the people. Like the first 7-8 years I was in Apple, right, the silicon produced is very poor quality. So even with this kind of company, with the will, with the money, it takes a huge amount of time to train the people able to execute. So that's why I think to make Japan as a successful country, not only you have to have the hardware, but you also need the software, which is the person, right? So you need to train from young generation. I talked to one of my designer in Japan. He graduated from Euro Tokyo. I asked him, say, okay, does Euro Tokyo has a program? Actually, you're really going to write in Verilog using PD synthesis, right, produce a chip and tape it out. I graduated from Euro Michigan, right, 1998. We're going through all that, right? We do Verilog simulation, we do synthesis, we do cadence PD, we tape out the chip. So after I graduate, I know everything. Not everything, but just I'm familiar with the flow, right? So we're pretty well trained. So if Japan really want to begin to this, it had to be starting from school, right? So you need to have very close tie with the industry, building the highest end possible, right? Design, train those people. And 10 years from now, you maybe have a good design team, right, with a good leadership. So you have to do that fundamental change. So answer your question, right? Capital is not an issue, anything is not an issue, but the people is the most critical thing, training those people.
Thank you.
Any question? Yeah, so just feel free to reach out to me if I have any question you want to ask. Thank you.
Thank you, Mr. Lien.